Then, okay, pyroelectric materials and devices. The first fact we have to address is a basic explanation of pyroelectricity physical phenomenon. Pyroelectricity is a term that was first used by David Brewster while studying aeroshell salt in 1824. It comes from Greek words pure, that means fire, and electricity from fire. Its physical origin is the dependence in some anisotropic materials of polarization, electrical polarization from temperature. On the right, you can see the so-called Heckman diagram that shows the correlation between electric field temperature and dimensions that can be reversible in crystal. The fact is that even if this phenomenon has been widely exploited, there is still a not completely explained phenomenon, because it's difficult to decouple it from piezoelectricity and thermoelasticity, also due to the interactions you see in the diagram. The pyroelectric effect is due in detail to the association between the displacement field D and temperature variations. As we know, a variation in displacement field can originate a displacement current. A displacement current is dependent from electrical polarization through the relationship here described. But polarization, that is explained as the mean in a volume of all the dipole moments in a material, can be separated in two contributions. The first one is induced polarization, and is mainly due to electrical field. The second part is a spontaneous polarization and is intrinsic in the order of the material. Then, if we want to calculate the displacement current in our material, we can separate the contributions between the electrical field and the spontaneous polarization. And if we null the electrical field at the ends of our material, the only contribution to displacement currents is due to spontaneous polarization. Then, because of spontaneous polarization depends to a variation in entropy in the material with the temperature, we can estimate the pyro current as the first derivative of pyroelectric polarization, spontaneous polarization in a material versus temperature. If temperature varies in time, and the temperature varies with this, we can, in the absence of electric field, or if electric field is constant, and in a constant condition of stress on material, there is a coefficient P that is called pyroelectric coefficient, that can give us the relationship between the pyroelectric current and the variation over time of temperature, according to this formula. In a pictorial view, what we can see is a material that has a randomic orientation of dipole moments, but a preferential orientation, if we mean every dipole moment in a material. If we apply two electrodes, the charge in conducting plates reorder in order to null the electric field, then a current could not flow through the material or through an external circuit. But if we heat up the material through an electrical, through a thermal flow, our dipoles become more messy, more disordered. Entropy increases, and some of the charge that has been accumulated on the electrodes need to redistribute again to null the electric field. This transient current is a pyroelectric current. The same thing is when we cool down the material, entropy decreases, the material will restore its order, and the current, a negative current, will be restored into the device. Then we talk briefly on materials and polymers for pyro applications. We are talking about a vast class of materials that are dielectrics. We want to, that they could be dielectrics because pyro currents should flow not inside our material, but outside in an external circuit. In the field of dielectrics, pyroelectrics are materials that have a polarization that depend on electric field. Then the application of electric field could increase the polarization. Among pyroelectrics, we have piezo-electric materials that can accumulate surface charge if a mechanical stress is applied to our materials. Then in the among piezoelectric materials, we have the inclusion of pyroelectrics, that are materials that spontaneously have a polarization. Among these, there are some kind of materials that are both piezoelectrics and pyroelectrics that are called ferroelectrics, that where their polarization can be persisted through the application of an electric field and can be also switched. Then the best class of materials to do energy harvesting is ferroelectrics, its best case. But we are interested to pyroelectrics. Ferroelectrics are always pyroelectrics, but is not guaranteed that a material that has a spontaneous polarization can be switched by an electrical field. Then pyroelectrics not always are ferroelectrics. Why we have a variation of polarization? Because the material approaches to a phase transformation. Phase transformation that is well described by Curie point. By approaching from the lower temperature to the Curie point, the electric constant will increase because dipoles could orient more easily under the effect of an electric field. This is due to the change of the polarizability of the material. Then we have an increase of the rate of polarization versus temperature, and then an increase of pyroelectric coefficient. Simultaneously, we can detect this transformation also if we measure by calorimetry the thermal capacity of our material. Then the effect is, approaching the Curie point, is a change in the pyroelectric coefficient. How we can detect through electrical measurement this phase change is doing electrical displacement, electrical field measurements. Then, in presence of a ferroelectric material, that is the preferred class of materials for electroactive application, we can detect a remnant polarization that for pyroelectric material is the spontaneous polarization. A variation with the temperature of spontaneous polarization gives a non-null pyroelectric coefficient. When the material will transit through the phase change, we will see that this hysteresis will null itself, and the material will lose its ferroelectric and pyroelectric and piezoelectric properties, switching to a paraelectric behavior. Pyroelectric materials can be of all kinds: inorganic, organic, single crystals, ceramics, polymers. They are anisotropic because they need to have a preferential orientation. They range from the family of perovskites, lithium niobates, and other ordered materials. But it's important to underline that there are also polymeric materials that have the great advantage to be flexible, resistant to a mechanical strain, have low density, are biocompatible, and are easy to process at low cost. Then they found applications in sensors and also in energy harvesting. among the polymers, the pyropolymers, like polyvinyl chloride, such kind of nylons, vinylidene cyanides, and their copolymers, the main polymer is that is studied. There is PVDF, that is polyvinyl fluoride, that is studied, mainly studied because it has a very strong piezoelectric and pyroelectric coefficient, and they are known the techniques to process it. We go more in detail. Why I cannot change? Yes, PVDF properties depend from the presence of its polar phases, because PVDF, they are known five phases, crystalline phases of these materials that own their polarization to the orientation of CF dipoles in its chains. The polar phases are the most candidate, in particular beta phases, are the most candidates to pyroelectric and piezoelectric applications. How to obtain these electroactive phases has been summarized in 1989 in the work of Furukawa in two big categories: Pauling-induced orientation, that can be done on material, on dipoles, and uniaxial orientation on chain molecules. This gives ferroelectric polymers, and if shear strain is incorporated after deformation, we get pyroelectricity. We go in detail in Pauling. Pauling is the orientation of the material under the effect of a strong electric field that in PVDF usually changes the alpha phase in beta phase, and cold drawing will persist this orientation. There are some kind of PVDF copolymer composites like TRFE that can possess this property also without the necessity of a Pauling process, but Pauling is very, very well studied. Pyroelectric devices. A pyroelectric device is substantially a capacitor that has the ability to absorb heat. One of the two electrodes of the capacitor can be equipped with a heat-absorbing layer. Even as an example, if the capacitor is irradiated by light or infrared radiation. The simplest models for these devices are of thermal kind and electrical kind. A thermal kind model is changes the heat flow through a thermal resistance and heat capacitance into variations of temperatures. Variation of temperature can turn in variations of current in a controlled current generator that possesses an internal resistance RP and a capacitance CP. This simple model explains us that we need impedance matching in order to gather the maximum part of the electrical power from our device. If we want to characterize a pyroelectric device, we can do this in four different ways: by collecting charge, the first one, by detecting capacitance changes and then detecting the change in polarization, by using the inverse effect of pyroelectricity that is called electrocaloric effect, and estimating the heat flow from the device, and by the detection of emitted radiation of the device. But the preferred one is the first, charge or current detection. In ENEA, we have a setup that can do this, a very simple setup that works like a cryostat, a small cryostat that can do very controlled thermal ramps and very quick thermal ramps. And the systems that does co-registration, that is equipped through a electrometer that collects current from the device and co-records temperature and current with a sampling time that is shorter, very short if compared to the transition in temperature. Then we have raw data of temperature variations that have to be correlated to current density. In theory, it's easy to compare these signals because if we have a temperature square wave, it can be related easily to a current pulse. Or if we have, if it is difficult to have a square wave in temperature, we can do thermal ramping like us. But it's not easy to decouple piezoelectric from pyroelectric effects because the material can have a dilatation, have an increase in its size. Then it's important the data analysis afterwards, the measurements. Then, in order to conclude, we have pyroelectric devices that obey a simple rule to get pyroelectric current. The pyroelectric current magnitude depends on the surface area, but does not depend from device thickness. Then we want very large devices, but we can have very thin devices because performance does not depend from thickness. Also, we need a very good harvesting circuit for the power, the impedance adaptation, but also the ability, as in this case, to collect current transient in the positive and negative direction. Then we need a bridge with an adapted load. This is a small introduction. As a conclusions, we can summarize everything. We say that pyroelectricity depends on spontaneous polarization variations with the temperature. Spontaneous polarization is due to electric dipole inside the material, then it's a property of the materials. Pyroelectric current will vary with the temperature variations proportionally through the pyroelectric coefficient that itself varies with the temperature. We can have many pyroelectric polymers, but the preferred one is PVDF and its copolymers because of its performances. And pyroelectric devices should be carefully adapted to the external circuit in order to collect their electrical signal. Finally, I want to thank you for the patience, for the hearing me. I want to thank the team working on pyroelectrics in ENEA and all the nanomaterials and device group in ENEA. Thank you so much.